Okay, so we have this equation that says how much time has elapsed based on the half-life of a material and the initial and current amounts of that material. And this radioactive decay, remember, it's not affected by environmental factors. You can't speed it up or slow it down with temperature or with chemical environment or anything like that. And so it makes it actually a really accurate chronometer. We can use the rate of radioactive decay to measure time intervals. It's so reliable, and half-lives can extend into the millions and billions of years, and so it's really our primary technique for measuring the age of things like organic samples that have been preserved or even rocks themselves. The way we do this is by observing the half-life of a radioactive isotope. The half-life is well characterized and it doesn't change, and it applies to all samples of that isotope. And then in a sample that you wish to date, you just need to find this ratio, n naught over n, and that's able to give you the time. So I've got a slideshow image here that unfortunately figure 20.8 in the textbook looks a little bit different. But if we consider radioactive decay from the yellow parent isotope to the blue daughter isotopes, here we have a small sample of 16 atoms. At time 0, in other words, when the sample is brand new, then you're going to have 16 parent atoms and 0 daughter atoms. Then those numbers got scrunched up, so over that, oops, wrong side. I'll kind of mark things with my head here. After this first step, one half-life has elapsed, and there should be 8 parent isotopes and 8 daughter isotopes. Oops, wrong way. Okay, and one more half-life has elapsed, and now there should be 4 parent and 12 daughter isotopes. And then one more half-life, there's only 2 parent isotopes left and 14 daughter isotopes, and then one more half-life, it's 1 and 15. So we can look at a sample, and let's say we note that there are 4 of the parent isotope left and 12 of the daughter, and we'll say, oh, 2 half-lives have elapsed, and depending on what the half-life is, that means, you know, it's 4,000 years old or whatever. So we'll get rid of that bad figure. And this whole process is called radiometric dating, and there are 2 different ways and types of problems that we'll investigate with radiometric dating. So the first one involves the decay of isotopes over geological timescales. So uranium-238 will decay to lead-206 on a scale of 4.47 times 10 to the 9th years. Now you may recall that U-238 has a whole series of nuclear reactions that occur, but after that first step, uranium, I believe it's to thorium, all the rest of those steps happen really quickly. So on the scale of billions of years, basically as soon as a uranium begins that process through the radioactive series, it'll rapidly end up at lead. And the idea is if you have a sample, well, lead and uranium are different metals. They've got different densities. They're formed in the earth under different conditions, and they gather and aggregate in different strata of the earth. And so if you have a sample of uranium metal, a rock that contains uranium, and you find some lead there, then we can infer that that lead wasn't there from the beginning. It's not primordial lead, but rather that lead is the result of uranium decay. And we can look at that ratio then of the daughter and the parent and date the rock to see how many millions or billions of years old it is. There's another, and this, again, this is a whole radioactive series. It begins with alpha decay, but you may recall there's, a dozen or so steps involving both alpha and beta decay. Another isotope that is useful is potassium decaying to argon. This is a beta decay process, and it's only a single step. And potassium has a half-life of 1.250 times 10 to the 9th years. And so it's also on the order of 1 billion years. One problem with this is that argon is a gas, and so any sample that has been exposed to the air, that argon is going to escape. But it's one of the noble gases. But if you have a pristine rock sample, the potassium in the rock should be held in airtight pockets, and you can crack it open basically and try to find the amount of argon that is in that rock, compare it to the amount of potassium that's in the rock, and figure out the date. So let's look at an actual practice problem. All right, so if we have a rock that is, let me erase some of this actually. Okay, so suppose you have a rock sample and it contains 5.5 grams of lead, and it contains 29.6 grams of uranium. So we can see that some of the uranium has decayed to produce lead, but we can't just use these numbers to compare directly, because when uranium undergoes that radioactive series, all those alpha decay events are shedding protons and neutrons. And so the atomic weight of the lead and the uranium are different, 238 versus 206. And so on a gram for gram basis, they have different molar amounts. And what we really care about are the numbers of moles. Okay, so give me a second. So the lead is 206 grams per 1 mole, and that's going to be 0.027 moles of lead. And the uranium is 238 grams, and that is going to equal 0.124 moles of uranium. And the problem is, this is the number for N. So we can start writing that equation. We've got T is equal to the natural log of 0.124 moles. But what was the initial amount of uranium? Well, everything that is lead used to be uranium. And so we'll just sum these two numbers together. 0.124 plus 0.027 is going to be 0.151 moles of uranium initially. So we'll put that number right there, 0.151 moles. So you see that initial amount is the daughter isotope number, moles of the daughter isotope plus the moles of the parent isotope at current time. And then, the half-life is 4.5 times 10 to the 9th years. We'll put natural log of 2 down there. And in the end, that is going to equal 1.3 times 10 to the 8th years. Or in other words, 130 million years. That's how old your rock is. So, go ahead and erase that. There is another useful radioactive isotope that we use to date organic material, and that is carbon-14. So carbon-14 will decay through beta decay to produce nitrogen-14. And that happens on the order of, well, now I've forgotten, 5,730 years. So half-life is equal to 5,730 years. Which is really great because if we're looking at artifacts, wooden tools, or domiciles built by humans, then thousands of years is a really useful number for archaeologists. Or if we're looking at other organic samples like tissues from Australopithecus or something like that, then 5,000 or 6,000 year half-life is going to give us a good range of tens of thousands of years that we can accurately measure the age of things. But one of the problems is that the product, the daughter isotope here, is regular old nitrogen-14. That's the most common and stable isotope of nitrogen. And so if you take any sample of organic matter, you're going to find that there's nitrogen all around it, if only because there's nitrogen all around us in the air everywhere. So we can't do the same technique where we look at the amount of the decay product, because the decay product is literally everywhere around us. It is the atmosphere that we breathe. So what we do instead is recognize that carbon-14 is actually only produced naturally in the upper atmosphere. It's cosmic rays that will collide with the atmosphere and produce carbon-14, and those cosmic rays get blocked in those upper layers of the atmosphere, so no carbon-14 is generated on the surface of the Earth. And that means that and also the rate of production of carbon-14, because it's a cosmological event, is very steady and predictable. It doesn't matter what happens, the dinosaurs can rise and fall, there can be volcanic activity, there can be humans now beginning to industrialize, and all of that is not going to have a strong influence on the rate of carbon-14 generation in the upper atmosphere, which is kind of above all of that. And so it makes a really convenient radioisotope for us to study. If we assume that the rate of carbon-14 generation was constant, then the amount of carbon-14 that organisms will breathe in and incorporate into their bodies is going to be constant as well. I breathe in carbon dioxide and I breathe out carbon dioxide that plants will turn into their cellular structures, and then I eat those plants and I turn that carbon right back into my own tissues and things. So the bottom line is that we assume that the living biomatter of today has a certain concentration of carbon-14 in and amongst all of the regular carbon-12, and that rate of carbon-14 is all carbon that was incorporated into the body while alive, because it originated in the upper atmosphere. And once I die, for example, my carbon-14 in my bones and my tissues is going to begin to decay, and it will not be replaced because I'm no longer building up new tissues. Anyway, and so what we're going to do is recognize that living biomatter today has an activity. Living biomatter has an activity of 15.3 disintegrations per minute gram. And so you can actually calculate your own mass and have a good prediction about how many radioactive disintegration events are happening inside your body every minute. It's a lot more than you might have suspected. And we'll look at the activity of dead material. And the activity of living material goes in here as N0. The activity of your sample of dead material goes in here as N, and we can solve for the time. So let's look at a practice problem. Okay, there we are. So an ancient wooden tool exhibits an activity of 14.4 disintegrations per minute gram. How old is this wooden tool? So we'll say that T is equal to the natural log of 15.3 disintegrations per minute gram over 14.4 disintegrations per minute gram. And remember, those activities are proportional to the amount of radioactive isotope, and so we can use the ratios of activities just like we can use the ratios of masses, or we could use the numbers of isotopes themselves. And the half-life is 5,730 years. We have a natural log of 2. So we put that in our calculator, pretty straightforward calculation, and we get 501 years old. Now, carbon dating may seem like it relies on an awful lot of assumptions, but we also have access to actual samples that we know based on historical record or geological records or by some other method. We know how old a certain piece of wood is or a certain tissue from an animal. And so when we're able to figure out the age by some other means, we'll always compare it to what carbon dating predicts, and they support one another. It seems to be consistent. And so if we find a sample that we don't know the age, well, because it works consistently with all of these other known samples, then it seems reasonable to apply the radiocarbon dating to samples with an unknown date. So that's it for section 20.4 on radiocarbon dating, and we'll get into fission and fusion tomorrow.